Turn on the system now. Turn on the okay. Yeah. Wait a second here. Let's see, make sure. I'm not sure if it's just making it to the. Unfortunately, because of the semester is Burkhard, his apologies, and Matthias is teaching. So,
all right.
They send their excuses. There. Okay, so let me begin, since it's now the time. So I wanted to welcome all of you back again to the online SPICE-SPIN+X seminar series organized by the SPIN Phenomenon Interdisciplinary Center that I run together with Karen Ebersosite, that's now a professor at Duisburg, and in collaboration with the Collaborative Research Center SPIN+X, led by Martina Schliemann and Burkhard Hillebrands in Kaiserslautern and Matthias Chloe in Mainz. So as you all know, this is a Zoom webinar format, meaning that you will see the speaker and the person that is in the panel speaking, and you can ask questions, raise your hand, and I can promote you later for Q&A after the talk. If it is an important question, you can write it in and I can ask during the talk as well if it's important to clarify some aspects. The talks are on the Wednesdays, 3 p.m. on German time. And we have already the schedule for the full until the end of the year. Please encourage you to check it out and see it on our website. Just for today's speaker is Hide Kurebayashi, a professor at University College London, when graduated from the University of Cambridge, BC in 2010. Hide is an expert on spin transfer phenomena. Particularly, we had a nice overlap studying spin Hall effect with light and many other effects in the time while he was in Cambridge and I was in Texas. But now has become focused strongly on magnetism and spin dynamics in two-dimensional van der Waals systems, the coherent coupling in magnon-phonon hybrid systems, and has a very recent, beautiful review in Nature Materials. So with this, I'll stop sharing and ask you, Hide, to go ahead and share your screen and start whenever you would like.
Okay, thank you very much, Jairo, for the nice introduction, and also this opportunity to present our work. Let me just try to share my slide. Okay, thank you very much. All right, so just moving things here. Good. Right. Okay. Thank you very much. Opportunity to for this giving our latest result, particularly on this a van der Waals systems chromium German telluride, and we try to control this magnetism by carrier doping, both in electrostatic way and also chemical doping. And if I have a time, I'm going to show you the latest results of magnon photon coupling with this a superconductor resonator and also this material called chromium German telluride. And this project has been performed or carried out by the multi-institutional collaboration, including our team in UCL and also a Gorky Edders group in NUS. And all the results have been produced by young, excellent researchers. I just want to name particularly just Ivan, who did a lot of transport and gating experiment at NUS. Seik and Christoph did a fantastic experiment in the spin dynamics of this chromium German telluride at UCL. Okay, let's get started. I already just outlined some of the result that I wanted to share. And before jumping to these results, I just want to share my view of why this 2D van der Waals system are exciting and what we can do with it and which kind of potential it has as a research object. So let's get started in item 1. All right, so this is just a cartoon to illustrate what it looks like as a 2D van der Waals system. It's nothing but just a simple layered system. It has a van der Waals gap. And the difference between this and the graphene, for example, is obviously it has a typically 3D transition metal, ions or elements, and it has a finite magnetic moment because of the local Wundt rule. So that typical one is, for example, chromium A3+ state, and it has some octahedron a crystalline splitting. And if you're trying to populate 3 electrons in this state, and then we have a 3 spin polarized electron in one band, T2G band, and that can create a local magnetic moment. And if you have enough coupling between local chromium ions or moments between these two, then we can drive a long-range order, either a ferromagnetic state or antiferromagnetic state. Right, so that's the just kind of picture that we have. Then I just want to make a few comments on why this line of research would be interesting and exciting. And just from the material science side, what we can tell you is probably many of us are from the spintronics background, and then typical growth technique is either, for example, sputtering or MBE, so that we can really nice, a ordered or really flat layers. That's the aim of, and that's the state of art that we have developed over the last couple of decades. And here, I just want to look at the dynamics. Normally, when you do that, you just really spattered, let's say, target, and you can just really decompose everything into the atoms or dimer molecules, and then that can run on the a substrate or underneath layer underneath, and then that has a local thermodynamics and kinetics. That's the growth mechanism, and that can create some constraint. For example, you cannot make a very flat surface if you want to grow metal on a semiconductor or insulator, for example, because of different, different wetness. And also, if you want to grow epitaxial films, and all the things we have to worry about, it's just the lattice matching, so that we can make a lattice on top of each other. So that's a typical thing that we can think of. But when we look at, so this is the van der Waals growth technique, for example, popular one is a mechanical exfoliation. Then what we can think is that the unit of the growing a material is not just the atoms or the dimers. So that is thermodynamically ordered film or layers, and they can put on top of each other. So what we can do with it is that when you put on top of each other, there's a less constraint about thermodynamics and kinetics, where therefore we can artificially or create a different heterostructure on top of each other. And also, if you want, this is a typical, or this is a popular research area that in the condensed matter physics, you can also rotate, which we cannot do anyway at all by doing growth in this, for example, sputtering the MBE systems. So that's a really allow us to have a very significant, covering the parameter space in the material science. And with that, we can make really new transport phenomena, or even just magnetism that we cannot naturally get it. So that's the kind of motivation of 2D material research in general. And when we look at spintronics, we can say a bit more about it. For example, in spintronics, I think everybody can agree with that. This is pretty much driven by the interfacial effect, either spin-dependent scattering at the interface, or some exchange interaction, or even just spin orbit effect happening at the polar geometry, or just happening from the interface. And also, if you want to increase the proximity effect, you want to minimize the thickness, so that any just a measurable effect, transport, or even just magnetism can be governed by something from the interface. So you want to reduce the thickness. And again, that these material systems can be perfect a material group to achieve some of these goals, or probably all of these goals. Now, just looking more application-wise, one of the still exciting application from spintronics is the making of the memory. So if you think about just making the memory by 2D van der Waals systems, then what we can notice is that what we can notice by just looking at this is simple phenomenological Magnetic spin picture to describe the switching. So this is how much current density required to switch one of these layered magnet or moment. So just looking at the numerator side, there is a product of magnetic moment and also the thickness. Again, if you are able to stabilize this magnetism in truly 2D systems, and that means we can minimize this thickness. And also typically it doesn't have a very large magnetic moment. So that means by looking at this equation, that's really help us to reduce this current density or switching current density. On top of that, and in the denominator side, what we can tell you is that this is the efficiency of how much we can generate the spin by current. So this is the important parameter, for example, the same as pretty much like effective spin Hall angle. And the question is whether the spin Hall angle is strong in a 2D van der Waals system. The question, we cannot answer yes or no at this stage, but what we can tell for sure is that because of the raw symmetry of the van der Waals system, these are pretty much not cubic anymore. Then we can produce lots of different a spin orbit torque time allowed by the symmetry of the system. Here is just a table. You don't need to look at it very carefully, but just you can probably look at this review paper to be published soon or archive. So what we can tell you, what we just illustrate here is that we just pick the different van der Waals magnet and then add a polar symmetry, because when you make it thinner, it's inevitable that like the environment from top and the bottom part is different. For example, the effect of the substrate. So by doing so, what we can tell you is that we can make lots of different spin orbit time from the bulk symmetry or interface symmetry. I just pick up a particular material. So this is chromium germanium telluride, and this is just effective field when you apply the current. And what we can tell you from here is that normally, because of polar symmetry we add, we create some kind of chiral spin texture. This I just show you just one subband of this. Then you can create it, and that can create effective magnetic field when you apply the current. And that's current. This field direction is perpendicular to the current in plane. Now, on top of it, we can also generate additional time. Now, just looking at carefully, this direction J, this is just current direction. That means the effective magnetic field is parallel to the current. And that can just draw a simple just spin texture like this, a sunflower type. So that can be additional term that can boost this spin orbit term on top of some component of the plane somewhere here. Okay, so that what we can try to say is that because of the raw symmetry, we can generate really interesting spin orbit term, and that's the area that we can go into and then see whether we can maximize these effects to create efficient memory devices. Right. So then just give you some flavor of which kind of materials we can use. So just to pick up the typical or popular material that we are used since they discovered that we can exfoliate and then we can maintain the magnetism at the few monolayer regime. So these two are insulator, and this is ferromagnetic. This can provide a ferromagnetic order. You can see that we exfoliate it down to a few monolayers. We can still maintain kind of hysteresis or some kind of a MH loop, looks like ferromagnetic order. And also this chromium iodide, this is antiferromagnetic in the thin film regime, and then that can produce a layer dependent, for example, magnetism as well. And while these two are insulator, we also have some itinerant metallic system, which is kind of ion-based systems. So we still have a variety of the 2D magnetic systems, so that we can just, pick up the one that we want to work on, either insulating regime or metallic regime for applications. So then I just dive into a particular result or particular project that we did in the last few years. The first one is the electric field control of this a chromium germanium telluride. So we just make a FET device and then put the ionic gel on top of it and by default gating, and then trying to see how this a magnetism can be different depending on the carrier doping. So that's the idea. Right, so just to give you a bit of motivation, as I said, we have a lot of different materials available as a 2D bounded Waals materials or magnetic systems. And depending on the transport nature from insulated to metal, the exchange interactions are different, either super exchange, double exchange, and the direct exchange coupling between magnetic ions. And I just want to highlight that because typically in the past, in the spintronics research area, we're focusing on this metallic side because as soon as, for example, dope gallium arsenide manganese to create a dilated magnetic semiconductor, then this already creates this whole transport. Therefore, again, it's pretty much, it's close to this direct double exchange, but this is almost a metallic side. And also another a key development for this line is that we pick up the thin film of the magnetic layer and then try to gate and then against this film screening length. And again, this is already metallic. So there is no significant development where when you dope the magnetic materials from the really insulating regime and what's going to happen. So that's the motivation. And material of choice for us for this particular things is chromium germanium telluride. I just call CGT from now on. And this is ferromagnetic semiconductor or insulator. It's a relatively narrow gap semiconductor. So we probably just right to say the semiconductor. And exchange coupling is mediated by the super exchange regime. And also just a highlight that it has a outer plane easy access in bulk or undoped regime. So this is sort of the top view of it. And you can see that I just see this light blue a ball represent the chromium ions, and it can form the honeycomb lattice. And then between these two, there is a tellurium atoms like that. So the magnetic coupling between these two chromium atoms is a bit far, weak because distance is too far. But it is possible to generate magnetic coupling through this tellurium atom. So that's what we call exchange, super exchange interaction. So I can walk you through, because this is a bit more like a specific, and many of us are from spintronic background and we just work on itinerant systems. But I thought that it's nice to share some of the basic understanding of how we drive this system. And then that's actually related to this study. So when we pick this, let's say this 2 chromium atom and 2 tellurium atoms, and because of this octahedron bonding, and then this is corner shared, then the angle between these two is pretty much close to 90 degrees. And chromium has a, as I already explained, we'll just show the next one. Okay, chromium has a 3 plus ionic state, and then tellurium has a 5p state here. And because of this orbital nature, orbital symmetry, if you try to couple this T2G state to this tellurium P state, for example, this elongated along X direction, it is impossible to couple, but still we can have a final coupling between the Y direction, but that's pretty much weak, normally we call it. But then the driving mechanism of exchange interaction is actually interesting. I just follow the mechanism presented by Watterson et al. based on their RPS result. So what happens is, while this is a ground state, we have an excited state where we send one electron from the tellurium 5p states to the EG state, and then you have another to the EG state. So this is actually in the conduction band. And what happens here is that because there's a tellurium Hund rule where we want to align, or we want to polarize this S as big as possible, that's a first rule, that we want this sign of the spin polarization has to be the same for these two spins as described here. Now, and then we also have we have local chromium Hund rule. We try to polarize the same direction as the TEs, and because of this mechanism, and we can just drive the exchange interaction as a whole. So that gives us the mechanism of super exchange interactions, and that can give us just a long range order, in this case, ferromagnetic order in the CGT. And then now the simple question here is that when we dope this system, now this is more like a charge transfer mechanism. You have to excite largely on this big gap. But when we have this already electron on the conduction band, how this exchange mechanism behaves and what we can get as a result of this. So that's a specific question we have for this particular project. Right, so just to have just a quick mention of the previous work. So this similar study has been done by one et al., and where they use this silicon oxide as a solid state gating capacitor and using the back gate, and they try to measure a magnetic property by the magnetic optical effect. So this is a car rotation signal as a function of magnetic field applied out of plane. And then what they observed is a very, very subtle change of the magnetic, car rotation angle, which should be proportional to the magnetization. So that's what they observed. They didn't see anything in the change of the Curie temperature or in the change of the magnetic anisotropy. And what we know, we are doing the same thing at the same time, and we know that this doping level that we can achieve by this solid state gating is about 10 to 12 square centimeter. And at the same time, we just did the same experiment by using a different gating mechanism. And then this ionic gel can normally achieve much higher doping carrier injection. And then that's probably two orders stronger than this. And then we just saw a very different behavior than this, which I will show in a minute. And just I want to give you some flavor of what we are doing every day. So this is just a grow box, and inside of this there is a microscope and transfer stage here, and this is just a zoom in image or picture of this. And then I can show you some just really quick movie about what we are doing inside of it, if I may. Here, okay, just switch off the sound. All right, so this is the things that simply we just do exfoliation inside of the grow box. Some of them are air sensitive, so it's better to keep it also, inside of the inert gas environment. That's why we are doing inside of it. And then once you've done that, we just transfer some of this onto the transfer stage, and then we try to manipulate the stage by using the game controller. So he's not playing, my student Charlie is not playing the game, but just actually seriously working on this lab. So then this is just on the monitor. So we have a camera in it. You can see it by the CCD camera. So then what we can try to show is that, nothing happened. Maybe just this, we can quickly go through. You can see that there is some flake sitting there. And then we just sitting just inside of this Hoover, just electric contact. That's what we are doing every day. Okay, so if you're doing a good job, we can just nicely place thin film within the bar or electrode. Then we can do some transport experiment. And this is just some schematic of this. We have a electric contact, and this is a CGT about 20 nanometer for this particular experiment. And then putting on the ionic gel and then gating on the side. And this is the source drain current as a function of the gating voltage. And you can see at the beginning, it's almost insulating. There is no current within there. But once we just drive it and apply the large, reasonably good electric voltage, then we can increase the source drain current. And then just going back to the bottom, just as you can see that if you're trying to go back to the opposite side, we couldn't achieve this one because of some chemical reaction happening. And I just mentioned that on this side, we are saying that this is an electron dope regime. So we just focus on this only just electron dope regime for this our study. And the other thing I just want to highlight is although we start just gating a 20 nanometer thin film, but because of the huge doping, and we can accumulate lots of charge on the surface, and we can make the thickness of the conduction channel, it's about 1 nanometer when you plug in the doping density and then just direct constant voltage, and then it quickly calculates this distance or width of this channel D. So this is interesting because we didn't start with like a one monolayer regime, but effectively we are sensing, or we just make a kind of closely to the electron gas by using this technique because of the large electric field we create by the ionic gel. Right, so then this is the resistance as a function of temperature. And as you can see, just this is a quick check. When we don't dope, and this temperature dependent looks like semiconductor. But when we dope, you can see the temperature dependent looks like becomes metallic. That's great news because then we really not only just changing the resistance, but also we can see that this transport is more like a continuous. On top of it, by using just a Hobart device, and we can calculate carrier density by using the slope of this between this Rxy and output magnetic field. By using this slope, we can just extract it that in a zero voltage regime, this is a very, very small whole dope behavior. But when we just dope electron heavily by, let's say, for about 4 electron volt, then we can get the large carrier density achieved. So that's great because we just turn insulating CDT into the conductive CDT so that we can use the magneto transport as a proof of the magnetism. So this is the transport resistance measurement, or the XX measurement, when we apply the magnetic field out of plane. So we just showed the 60 Kelvin results. It showed a nice hysteresis that guaranteed the magnetism. And they just go up to 120 Kelvin, and if we just go up to 180 Kelvin, we can still maintain the hysteresis. That means, strongly suggest that this material is still magnet at temperature of 180 degrees, which is very different from the temperature at 64 Kelvin as a Curie temperature bulk system or undoped system. Right, so that's exciting. And then also I just want to give a particular mention of this interesting magnetic resistance asymmetry or anisotropy. So when we rotate the magnetic field in plane, so we just moment is following this direction, we can see the magnetic resistance of about 0.1%, which is similar to the value that we normally get for the transition metal ferromagnet. However, when we just rotate an out plane, what we noticed was this value of the change of resistance is even just about 50 times bigger. And on top of it, when we apply the large magnetic field, like 9 Tesla, then it just becomes really almost like more sinusoidal compared to the one we get in the 1 Tesla. And this value is already much bigger than our magnetic anisotropy. Therefore, it's something to do with this transport, which is very strange. Depending on, or just probably strongly related to the dimensionality of this material. We don't know what's origin this, but I just want to share because some of you guys can probably give us some idea of how to explain it. And I just want to mention also that these kind of behavior can be also observed in the graphene system. Right, so let's go back to magnetism. So we can see that this switching mechanism is very, very complex because just as this jumpy behavior tells us some change of the domain wall depending and so on, but it's very difficult to use this, like macro spin to explain how it happens. Instead, what we take as approach is that we just decided to pick up some point in the magnetic field where just when you apply the magnetic field back and forth, and then when this point resistance merge, we decided that this is a point where external magnetic field fully compensate the internal magnetic field, i.e. anisotropy. So we use this as a parameter to analyze our result. So this is a pretty much closer to outer plane. And if you reduce if you just tilt this magnetic moment from the outer plane direction, we can quickly notice that this width of this hysteresis significantly reduced, and then that continue to in plane direction. That can be matching to some picture of this domain wall picture. It's nothing surprising because this is macroscopic sample, shall we say, micron scale sample, but it's nice to see that this is, the quick decay represent this domain wall, a switching mechanism heavily involved, and that was the things that we picked up by our magnet transport. Right, okay. And also that can guarantee that the hard axis of this material is out of plane compared to the in plane. That is different from a bulk sample. I'll come back to this point in a minute, but I just want to mention here. Okay, so this is a summary of this. So I just, this is a plot. So what we plot is now, we just measure the saturation magnetic field for the outer plane and in plane. And if you subtract this, that should be related to the anisotropy field. So that's a plot as a function of temperature. So what we can tell is as soon as we dope by electric field, you can significantly increase the Curie temperature in the higher temperature side. And if you keep doping it, we can also notice that this carrier doping can promote both magnetic anisotropy and also the Curie temperature in the upper side. Now, it's very, very different compared to the bulk materials or undoped materials characterized by Fmr experiment, where first of all, sign of this U is different, means that there is a switching of the magnetic moment anisotropy, and also, as I already told you, there's a significant enhancement of this Curie temperature. Okay, and this is a bit of just quick demonstration. So you can turn on and off by just applying the electric field, and you can see that we can kill completely by just increase the electric voltage, and then that's the switch on and off the magnetism by just electric field. Right, so just go back to the interpretation because I sketched out the magnetism or just driving magnetism of the driving magnetism of this system at the beginning. So in undoped case, as I already explained, so the driving mechanism is basically this, excited states of this one electron spin into the EG state, and that can, by doing that, we can get the energy gain of the front energy, and that can reduce the total free energy as a driving mechanism of the ferromagnetism. Now, if you think about the doped case, the critical difference is that now we put the real electrons in E2G band, EG band. So by calculating from the carrier density, we can tell that 1/4 of this chromium 3+ states is doped by the one electron and become chromium 2+ states. And on this regime, there is the additional exchange mechanism can be promoted. In particular, this is pretty much almost delocalized, therefore it can hopping around everywhere, either through still deuterium ions or just direct coupling between the individual or different chromium ions. So that can promote clearly, magnetic coupling between these two ions. And in particular, when we have an alignment between the conduction electrons and the local ion moments, then this electron can further delocalize, and then it can gain the kinetic exchange. Therefore, that can give us an additional driving force to form the ferromagnetism. So that's the intuitive picture of why, when doped, CDT becomes really high temperature, relatively high temperature ferromagnet. To support that, we also did a DFT calibrations, and just what I show here is a different energy between the antiferromagnetic state and ferromagnetic state, and subtracting these two states, and that can tell us something about the exchange energy. So, and then in line with our experimental results, when we dope electron, then we can really promote this exchange energy or increase the exchange energy. Therefore, we can get the large Curie temperature. Also, in a DFT, what we can do is that in a ferro state, we just simply rotate the moment 90 degrees, and that can tell us the difference. That can tell us the difference between energy of these states, i.e., magnetic anisotropy. And nicely, when we look at this energy difference, we can also see the sign switch of this value, meaning that easy access can be different for outer plane and in plane promoted by the carrier doping. Okay, so that's what I will show from the electric field component. And we can do the same experiment by chemically doping method. And the reason why we decided to do this is that when we just do the chemical doping, we can just differentiate these three different effects. So when we do the electric doping, we can create a charge. Also, we can create electric field. And also as a result, we can create like 2D confinement. So we don't know which one actually provides us the result what we get in terms of magnetism. Whereas when we look at chemical doping, simply just puts the alkaline atoms inside of this van der Waals gap. That's what we call integration in the chemistry language. We can do that. We can just remove the electric field component, the 2D confinement, and then just effect that we can measure is pretty much coming from a charge doping. So by comparing these two results, we wish to understand what this carrier doping does and what the other two does. So that's the motivation for this particular experiment. And just to give you quick result. So this is the resistance of the function temperature again, but in this case, we just put the sodium inside of this CDT van der Waals layer gap. And similar to the electric field one, we can see that, so this is an undoped case, but when you doped, we just reduced the resistance fairly well. And also we just show the different temperature dependence of the resistivity, not pretty much like a metallic regime, but just we are nearly there. And when we measure magnetic transport, now this is RX component as a function of in-plane magnetic field, sorry, out-of-plane magnetic field.
I'm sorry, Hide, can I ask very quick questions just for us, people? When you are speaking about this doping, what does this doping mean in terms of electrons per chromium? I have no clue whether this 1012 means 0.1 electron, 0.01 electron.
This is equal that way.
I can stop and answer. So this is, sorry, I didn't mention that. So
not about this one, sorry, not about the previous slide when you were doing electric field. This I understand. This is 0.3 is 0.3. That's clear. But
yeah,
what
sure.
about the previous?
Okay,
one?
So I can just quickly go back and spend a minute to explain it. So this one, the electric gated one. Okay. So what we saw is, first of all, we measure the carrier density by Hall transport. Okay, Hall effect, and by using this value and by using an assumption that this is purely 2D, single layer, we can calculate how much electron per chromium atom we dope. And then we by just simple calculation, we found that it's pretty much like a 1 in 4 electrons for chromium has been doped. Although this is just because this is delocalized, we couldn't just differentiate between these very easily. But we just say that 25% of chromium 3 plus is doped. Does that make sense?
Yeah, go ahead and continue.
You will give a number on the next slide, which is in 1012. So that corresponds to 0.25. That's just my very simple question. On the next slide, you gave us a plot.
Next slide. Here.
Yes, here, 10 to 14. So that is, how does the scale translate to electrons per chromium? Just one number.
Yeah, I can tell you that. So in the experiment, we found that 2D carrier density about 4 times 10 to 14 square centimeter. So, and then by calculating how much electron per chromium we have, and this is 25%. So we are looking at this regime.
Thank you. Very strange.
Okay.
Yeah.
We can discuss it later. Okay. So just quickly go through. I don't know how far I went through. I think probably just looking at here. So this is the magnet transport as a function of magnetic field. And you can see that this is some peaky structure we observed at 15 Kelvin when we applied the magnetic field out plane. So it sounds like, kind of switching behavior. We're not sure at that time, but things are getting clearer when we just study a bit more. I will walk you through that. So then I just measure, or just this is some plot of the height of this peak. Again, this is not at this stage clear whether this represents magnetism, but it's nice to plot. And then it just plot as a function of the temperature. And then that reduced as we increase the temperature, and then pretty much just disappeared when we hit the 200 Kelvin. So that's what it is. And whether this is related to the magnetism or not, I will come back to it later, but this is what we observed. And also the key measurement here is that not only just, so this peak behavior are different, or is different slightly in terms of the shape when we apply the magnetic field out of plane. So when we apply the outer plane, this width is larger, and compared to the one when we measure in plane, and the width is narrower. So what we can tell you, well, if this is coming from the magnetic anisotropy, what we can tell you is that it requires a large magnetic field to fully polarize your local magnetic moment along the magnetic field direction compared to the one that in plane. This clearly suggests that magnetic anisotropy is acting on an in-plane direction because this requires less magnetic field to fully saturate. So that's actually inconsistent with electric doping experiment as well, because we switched a anisotropy to out of plane to in-plane by the doping. All right, so then now we can compare between these two, that was the initial motivation. So what we can tell by just comparing these two is that carrier doping, which is the case for both cases, can increase the Curie temperature and also promote the switching of the easier axis from out of plane to the in plane. What's different is that the shape of this magnetic resistance curve. While this homogeneous, not homogeneous, it's just bulk doped regime, its switching is smooth. But if you look at thin film regime, switching is very, very jumpy. So clearly that is affected by this domain wall switching mechanism and other sort of things. And that's the interesting point to make. I mean, the other thing I just want to mention is that this size of the magnet resistance is the same for bulk regime. What I'm trying to say is that when you switch in plane, we don't see any magnet resistance this size. But when we do, if you remember, the size of the magnet resistance is very different when you switch out of plane up and down, and also in plane of order of like a factor of 50%. So clearly something we can tell by just looking at the two different results, and then we are really working on this point. Now, just moving on to the Fmr experiment, I just probably should speed up. So this is just, I believe that many of you know already the Fmr experiment, so I just skipped the basics. But this is just typical result when we measure the CGT undoped, and when we apply the magnetic field in plane. And this is a bulk result. So the shape of the peak looks like this archy dip shape. That's because this is the hard axis behavior. On the left-hand side, when we apply the magnetic field, we try to reduce this internal out of plane, uniaction and isotropy field as you increase a magnetic field, so that the spin wave energy goes down as you increase the magnetic field. But once fully polarized, this is an almost polarized regime. Now M and H is the same direction. Then you can just increase the spin wave energy by just increase the magnetic field. So that's the typical picture or behavior of a hard axis behavior. Please just bear in mind this. So then I just want to show you the doped case. You can see that this peaky behavior just simply disappear. We can see that this curve is just going down to the zero energy when you sweep the magnetic field. That's the easy axis behavior. Now the sign of this inside of this bracket is positive compared to the negative in the hard axis behavior. Again, this suggests the switching the easy axis when doped. On top of it, I just want to mention that not only just main peak, there is significant or multiple satellite peak, and that represent possibly, if you just look at this in the same film, we can say that this is probably just backwards volume mode, but this is almost a bulk regime, so it's very difficult to figure out what these are coming from. But again, these are open questions, but I just thought that it's nice to share. Right, so just again, temperature dependence. When you increase the temperature up to 150 kelvins, you can still see the nice archy behavior. And they just go up to 200, still there, 250, we can still see it. And it'll go at about 250 kelvins. And by just analyzing this position of the resonance field as a function, resonance frequency as a function of the field, then we can characterize this, for example, some magnetic parameter of effective magnetic field and so on. And also this is another proof that this is an in-plane magnetic case, because when you measure in plane, you can see that you just need a small magnetic field to reach resonance, but when you just bring that onto the outer plane, it requires more energy more magnetic field to reach resonance. So that's a nice proof. So we can tell that these are, when we doped, it definitely promotes the magnetism up to really high temperature. And I also show that this is not only 0.3, but this is 1.0 doped case. It's just a heavily doped case. We can maintain the resonance up to 250 Kelvin. But I thought that's really exciting news. But by just looking at again, kind of the resonance field as a function of the frequency, then we can tell that it's something strange, because when we reach the higher field regime, this value of the effective magnetic field, which is pretty much proportional to the magnetic saturation magnetic moment, it's floating rather than just changing as a function of temperature. So we think that at this regime, long-range spin order is gone, but somehow we maintain the short-range spin order somehow, and they still observe some effective magnetic moment inside, on top of similar to like an ESL response. Another thing I just want to quickly share is that line width as a function of field, so frequency can give us a very nice encouraging news, because when you just fit that with the linear fit, then we can extract the damping, Gilbert damping alpha, and this value is similar to what we observed in the 3D transition metal cases. So in that case, we can use these materials. I mean, this is just one example, but these van der Waals system is not bad as using as a like spin wave or the dynamic experiment. So that's that. And finally, I just spent probably 5 minutes to explain this one. This is just quickly flashing you the results, but I hope that can generate some interest and some of you from the audience. Good. The idea is very simple, because when you exfoliate the flake, so this is just some of the flake, you can see that the size of this flake is very small. Micrometer in the lateral dimension, the thickness is as thin as 1 nanometer. So that's the significant lower magnetic volume. And if you want to sense this small magnet by the dynamic experiment, you have to have a very small mode volume of the resonator. That's the reason why we just decided to use the superconducting resonator as a sensing mechanism of this particular kind. And so this is just a nitride spattered deposited on this pattern. And this is a particular shape of the resonator. And this width of the bar is about the micrometer. So that's similar to the lateral size of this. And this is an inductive coupling regime. And then we make it on the substrate, and then just connected it to a transmission line, and then we can see the resonance. And loaded resonance or Q factor is about 6,000. So this line width of about a few megahertz at the resonance of around 12 gigahertz. So it's a reasonably good resonator if you consider it on-chip resonator. Right, so I can show you this particular result. So this is the measurement when we sweep, or this 2D plot as a function of a frequency and magnetic field. So you can see, so this line represents the resonance frequency shift when you apply the magnetic field because of just simply the superconductive nature. And you can notice that there is faint region in the middle. So this is the region where magnum mode just overlap to this resonator mode. So then when we measure individual peak, so this peak, it had an individual peak in the magnetic field cut. And then when you analyze the line width as a function of magnetic field, you can see the beautiful Lorentzian peak. So what I mean by that can be explained by this simple cartoon or block diagram. So at this small magnetic field region, so this resonator is resonating, but magnet is not resonating at all. So if you inject the energy into the resonator to create the photons, and then that can simply dump into the reservoir by its own dumping mechanism. But when you hit this resonance, what's going to happen is now a CDT magnon start to resonate, and it needs to start to couple by the dipole interaction. Then we can see that start seeing the energy exchange between these two. And because the damping or relaxation of the CDT magnon is larger than this, so once we pump this system through the resonator, but pretty much all the energy is drained by this channel. That is observed is a huge increase of this line width from about 1 megahertz to 8 megahertz. So that can be actually, this Lorentzian peak can be fit by this Lorentzian behavior, and we can extract the coupling strength and also the relaxation strength or relaxation rate of the magnon as well. So that's something we can use as a tool to study the thin film flake. And I can quickly also show you that it is possible to measure the same thing in a 10 nanometer. By our eye, it is very difficult to see any faint behavior, but we can still see, computer can still tell us that the line width is sharply just increased at this thickness regime. And by just improving that, we can just go into truly like 2D regime to study the spin dynamics in the 2D van der Waals system. So I think it's time to wrap up. I just want to show that main results of this carrier doping and the carrier doping by the both electric field and also chemical doping. And we can tell that Curie temperature can be enhanced significantly and by the mechanism of double exchange interaction. And also accompanied by that, we observe this anisotropy switching, which is interesting to observe. And the second part is just a quick show of this magnon photon coupling and using the superconductive resonator and the flake. And we can use this as a tool to study the 2D spin dynamics, but also we can use this to study like more spintronics experiments such as spin pumping and other sort of things that we can use the direct coupling between the microwave and spin waves. And the final remark is actually about this point. Although we just learned something from this experiment, there are lots of open questions. For example, large magnetic resistance, and also its anisotropy when we make it thin, and also just complicated switching, and also like a spin wave resonance. Some of them are really unknown. So that can illustrate the richness of this magnet itself. And we can do something that we cannot do with a transition, 3D transition metal, but then we can use something doing this. And I just want to mention that this is just a result from a single layer of these materials. And then when we make a heterostructure, I can naively and foolishly believe that there's really exciting things will be happening. So with that, as a final remark, thank you very much for your listening, and I'm happy to answer any questions.
Yes, so thank you very, very much. We have an applause for you.
Thank you.
Yeah, so we have lots of questions that we're going to start with. So let's start with Vida Wu. Can you please ask your question first? Yeah, go ahead.
Oh, yeah, thanks. Thanks for the nice talk. Sorry, I might missed, but for the sodium dope box CGT single crystal, can you just measure magnetization simply to tell whether the TC get enhanced? I think you use the resonance FMR to infer the TC enhancement, which seems to me is much harder experiment.
Indeed, we can measure because that's a bulk sample. I didn't show you, but what I can tell you is that so there are two. I just want to show you. There are two carbs. One is just still like undoped CDT, and the other one is just some tailoring going down to the high temperature down to probably 200 Kelvin. So that represents the doped CDT. So the quick answer is yes, we can measure it, and I hope that we can show these results when we publish the manuscript.
I see. So maybe that's related to some other question, because what you described indicating there's some inhomogeneity, probably that related to the synthesis of the crystal, right? How do you do the
absolutely? So just I'm going to show you this picture. Intercalation, by just drawing the cartoon, it looks like homogeneous, but this is not the right illustration of this. It's just a blob of this alkaline atoms is just populating as an island. So there is no wonder that inhomogeneity can be created by that effect.
Thank you.
Okay, the next one will be Banan Kerry. Can you please ask your question? Unmute yourself. Are you able to talk? Okay, if doesn't seem to be, I can maybe ask. Michael, can you go ahead and ask Michael Farley? Can you ask your question, please?
Thank you for this excellent talk and these nice results. Just one comment first. You can determine the Curie temperature at a ferromagnetic transition with the critical fluctuations which you see in the FMR damping. So if you monitor the line width as a function of temperature, you might see the feature of critical fluctuations. But my question is, so when you do this doping, I would assume that you have strong spin orbit effects, which would mean that the G factor or G tensor should change in your material. Did you investigate that?
I see. Yeah. Okay. That's right. Okay. Thank you very much for the comment. Actually, I didn't for this critical behavior measured by the damping, and for this G tensor, G anisotropy by doping, we actually didn't investigate yet. Indeed, definitely, this is an excellent suggestion, and then we will definitely measure and then quantify it. One thing I noticed, and then also noticed from your review paper of the same film, so this gyromagnetic ratio, questions of gyromagnetic ratio is a good measure of G factor. I think I don't have a clear answer to yes or no, but at least we can measure this G factor anisotropy by using gyromagnetic ratio, anisotropy, and then we will.
You need to be careful in the interpretation. So this simple analysis holds only for D metals. So
Okay.
for your exchange coupled systems, it may be a little bit more tricky, but there are also models to discuss that at least.
I see. Okay. Yeah, I will look into that. Thank you very much.
Thank you. So let's make, I'll ask the question for Banan Curry, who cannot use his microphone at the moment. So how do you intercalate CGT with the sodium atoms during growth or after exfoliation?
Okay, sorry. Okay, so this is the chemistry part. So that's done by my chemistry, my colleague at UCL who does a strong background from chemistry. So what I can tell you is that there is a solution, and you just dip this pristine CGT, and then there is a chemical interaction or reaction. Basically, this is, sodium is soaked into the van der Waals gap. So this is purely chemical process. And then when we just take the solution and then pick up the sample and then measure. One thing I didn't mention, but once it's doped by its alkaline atoms, this becomes air sensitive. So handling of this material is very difficult. That's something really we spend a lot of time, but we managed to put this doped flake without exporting to air and put it inside the cryostat. But that's the things that we.
You further ask, what is the solution that they use? I think it's very.
I'm afraid. I
don't think you would know, unfortunately.
Sorry. I should know, but if you just email me about this question, I can respond that to you by collecting the information from my colleagues. That's as much as I can do.
Excellent. Let's do that. Very good. Then we have a quick question first by Seet Akbar in Bristol. Can you please unmute yourself and ask a question?
Hello. Can you hear me?
Yeah.
Yes, I can hear you.
Yeah. Just a quick question. So basically, you said you did gating, and then you also did chemically doped. But for the chemically doped sodium alkaline atoms, you had 0.3 and 1.0. I saw that. How does that compare?
Sorry, I missed the input.
Sid, can you repeat yourself? Sid?
It's just the final part, yeah.
The final part, I think he's still talking. I don't think he understood that at least I can hear him. Can you hear him? Sid?
I cannot hear.
Actually talk to.
Nobody can hear him, no.
Okay. So Sid, we cannot hear you. Can you, maybe we can read his question. Just a quick, Sid, are you there back?
Hello. Sorry.
Yeah, can you, sorry, we missed you right when you were starting asking the question. Can you repeat yourself, please? Can you repeat? Because we lost you completely. Okay, let's move on, and then while you fix your apparatus, it will be Daniel first, and then Igor, and then we'll go back to Sid to fix once he fixes his stuff. So Daniel, can you ask your question now?
Yeah, I have a question about anisotropy. It looks like when it becomes in plane, it is even stronger than original out of plane anisotropy. At least that was actually in one of your slides when it crossed zero.
Indeed, I can probably show you.
And why there may be strong Isaac anisotropy out of plane, we understand very well. That's actually mostly due to very strong spin-orbit coupling on tellurium. Super exchange goes via tellurium. But are there any idea, first of all, is it indeed true that in-plane anisotropy is even stronger? And are there any ideas why?
It is very difficult. This is probably the most important question that I want to understand. But then even just magnetic anisotropy in the bulk, or sorry, undoped regime, so insulating regime, it is not described by a single ion anisotropy. It seems like, by looking at the literature,
no, it's definitely exchange anisotropy, that's for sure.
Yeah. So yes, anisotropic exchange interaction because of this 2D nature, and then so when we dope, and then if we see anisotropy, in-plane anisotropy, it becomes bigger, and I have no idea why this value is even bigger than the one that we have in undoped case. I actually don't know how to look into it. So if you have any suggestion or any way to look in how to look into it, I'm very much looking forward to hear, because you're one of the experts.
Is this strong in-plane anisotropy already in a very conducting metallic state, or it is still in a relatively insulating regime? Because if it's in insulating,
okay.
then I could imagine, for example, that you create something like localized chromium 2+. Okay, it may behave differently from normal 3+. Normal 3+ have no single site anisotropy practically, very isotropic. 2+, I don't know, but couldn't it be that single site anisotropy starts to play some role in doped material?
Sure.
I don't know. I don't see it right away.
Sure.
It might be an option.
What I can tell you by just looking at this result. So this is just a low voltage regime, just 2.6 volt. It's already probably, oh no, this is not that case, but probably just looking at the height. In fact, yeah. So maybe this, we can say this is comparable by just looking at it, because this is probably 500, and this anisotropy field is it kind of more like close to 500. So that's the things that we can tell from the experiment. But again, I don't know how to explain that. The other thing I just want to show you is that some cases, it's anisotropy is almost gone. So it's basically, if you tune it, it's happened to be, we didn't carefully tune, but it just happened to have the material which has almost zero anisotropy there. So it's somehow a bit London, but that's something we can tell. It's not a significant jump from one to the other. There is some transient between these two switching. So the value of the uniaxial anisotropy is gradually changing through zero.
Can you also reach this regime of almost zero anisotropy for very thin films for 1-2 layers? Because
so that my idea was maybe at that regime you generate Marmin-Wagner theorem material.
Yeah, exactly. That's exactly
that's my interest, and we are working on this.
Okay.
So thank you.
So Igor, let's ask your question next.
So it's a little bit in line with the previous question. So if you go back to your Hubbard model diagram, then it's quite clear from that that any doping can only reduce tendency to ferromagnetism, because basically it's very simple. If you just fill your EG band completely, you get manganese 2+, very strong anti-ferromagnet. So that, as Daniel alluded to, the only possible way how this doping can make it more ferromagnetic is because of metallization, because of metallic effect, sometimes sort of of double exchange, and then it would be very strongly correlated with metallic conductivity and so on. Similarly, for exchange, again, as Daniel also pointed out, we understand very well how this exchange anisotropy comes for 3+ case, and it's Ising anisotropy. And then if you have band structure calculation, it's no problem whatsoever to separate exchange anisotropy from single site. And I don't understand why your colleague didn't do that. It's completely elementary. And that you can also see from that whether it's metallic effect or not. I mean, I strongly suspect that everything you see is related to metallization and nothing else, not on the level of this diagram, basically. And in fact, what you told us that it's very strong doping. I mean, it's really supposed to become very good metal if it's really that's 0.25 electrons per chrome.
I agree. So that was always the point of discussion, whether this, for example, when you dope one electron in this EG conduction band, I think Fmr level is within this band. That means that electron is fully delocalized, and then this metallic that can produce a metallic texture.
understand that microscopically from the calculations. I don't see why not. And other thing is, of course, that the other question that indeed the one thing that comes to mind, and because it's Morman-Wagner theorem, maybe somehow you reduce fluctuations, but that's a logarithmic effect, and it should be very weak. So you really have to modify your exchange coupling to get this strong effect that you have so far.
So the logarithmic effect in terms. So
yes, there is the here as well. Yeah.
Okay. All right. So.
Michael had a quick comment.
Yeah, I just responded. Yes, I had the generate here. Yes.
So it's a mistake on the plot.
Okay, so can you just please correct me?
He wrote it in the chat.
I mean,
oh, I
yeah,
see.
it's not. I mean, it's sort of like traditional tradition to plot them a little bit non-degenerate for visibility, but of course that's degenerate. Yeah.
Yeah. Okay.
Oh, you mean that's a P bond?
Let's make it clear.
The T2G, yeah.
Is wrong.
Yeah. So just the reason that I think the motivation of this case is it's basically these two sides is like a px py. And then just send, if you degenerate, we cannot tell this front row very nicely. So that's the reason why we just split.
Sorry, it's much simpler.
But that is actually a weak effect. This is this 90-degree Goodenough-Kanamori rule exchange. That's weak here. The main exchange is this the other mechanism that you mentioned, that EG to T2G exchange, because that's proportional to PD sigma times PD pi, and the other one is PD pi squared.
Okay.
All right. So just adding to that conversation, I just want to show you this Watson Edsford beautiful experiment. So this is our Fmr experiment, and then of the undoped CGT, and then I invite you to. I'm sure some of you have read it, but what's key here? Again, I'm not an expert of RPS and nor this correlated magnetism. When they measure the peak of this 5p EG band and then reduce the temperature, you can see that significant reduction of this energy. And then their proposal was that this is gained by the local front row, and that drives the ferromagnetism. So initially I thought that T2G and P pi hopping can be the one to drive the things, magnetism. But when you look at T2G state, we cannot see a significant change in the band position. So I still believe that this is a driving force, probably different from the typical Kanamori good enough 90-degree rule. But this particular materials, it seems like this partial charge transfer states can give more effect than the other. So that's as much as I can say.
It is the same effect, just described differently. You can describe Goodenough-Kanamori rules in the same way, and you will see the same effect.
Sorry, then maybe
and by the way, looking at this, I just realized that I think I know what happens in your system. What happens is that you just screen out Hubbard U, and it becomes effectively smaller. And because your exchange coupling is inversely proportional to Hubbard U, then by reducing Hubbard U by metallic screening, of course, you would increase your interaction.
Okay.
Okay. I take that.
Comment. So let's go next to Sarah. Ask a question. Can you please unmute yourself, Sarah?
Yeah, I wanted to ask if you fancy any structural change accompanied by the carrier doping in the material.
Okay.
Can that happen?
Okay. So sorry, I didn't mention that. That was. Let me just try to. Here. So first of all, this is a Raman spectroscopy, and we measure Raman while we are gating. So I can just walk you through. So this is a pristine state, zero doping regime. This is the original peak, vibration peak. When you dope it about like a 3-4 volt, we can still maintain the peak position pretty much well. There's a bit of subtle things, but line with broadening due to the carrier doping. But we believe that the structure itself is maintained as it were before. And then we just go back, we just make a cycle in this regime, it just simply come back to the original state. So by looking at that, we think that there is no structural change while gating So that's for the electric doping one.
What are the two peak close to 200 centimeters minus 1? That seems to broaden, can almost
You mean
disappear.
200 here?
Yeah.
Sorry, I cannot tell you what it is exactly from
Okay.
this, but I can look into it.
Okay. And what about the intercalated compounds? Could you characterize structurally the change?
Indeed, yes, we did it by the X-ray and also Raman, and then again there is a subtle change of the position, but there is no significant change in the peak order and so on. So from that we can tell that there is no significant structure change. That's as much as I can tell. Sorry, I don't have the data. My students got it, but
okay, thank you.
Thank you.
Excellent. So we go with Igor, and then we'll try again Seed after that.
Can you hear me?
Very low, Igor. Can you speak up, please?
Yeah.
Okay. So my question concerns. Can you hear? Yeah, right?
Yes, I can hear now.
Okay. So question is why this ion gel is 2 order more efficient for doping than just solid state. And question is also whether you measuring not only your film, but together whole system.
Sorry, just
gel plus film.
So J is the exchange coupling strength. Am I correct?
Yes. Well, possibly, it may contribute to exchange coupling and also to anisotropy because you have ions there. And
yeah,
it is a very strong Coulomb interaction.
That's right. So indeed, so this is what we call, I believe, that's anisotropic exchange interaction, and then that can indeed create the anisotropy. So, sorry, just I didn't catch the question very well, but what was the first part of the question you asked?
First part of question is why ion gel doping is much more efficient than solid state one. So two orders of
Okay. So sorry. Okay. Got it. Sorry. Let me just go back to it. It's simply, okay. So I've got it. So here, for example, so like it's probably easy to say if this effect is a linear response. It's probably very crude to say. We just can increase the carrier density 10 times, 100 times more, right? So that means that if this effect is linear to n, then our effect is 100 times bigger. Just this is very, very crude way of doing this. So just the more electrons, the stronger the effect is, and the strong impact on J.
And are you sure that all these ions do not penetrate your film?
Are we sure that these ions are not?
No.
Sorry, I didn't.
Gel ions can penetrate or influence surface of your film.
Yes, that's a very good question, and we don't have a clear answer to it. For example, just by showing the Raman, we didn't see it in as a Baruch response. So therefore, we have some certainty that it doesn't significantly cause a problem. But one thing we can tell, well, for example, so this FGT, if you dope with like a lithium ionic gel, in fact, all the effect is coming from the lithium intercalation. So this is the electric field intercalation by that. So, but then for our case, I think that there's a question that's what this ion or ionic gel does. at the surface, but this is something we cannot observe locally. So unfortunately, I don't have a clear answer to that, but I'm slightly optimistic that it doesn't do much, except for, there is a clear, well, one thing that I mentioned, just it's already rumbling around, but there's a chemical reaction when you dope or when you apply the negative voltage. So in this case, they create chemical reaction happening at the surface, but it seems like on the positive voltage side, this doesn't happen. So we wish that the main effect is just simply just charge doping or charge accumulation rather than anything else other chemistry.
Okay, thank you.
Let's try one last time for Seed. Can you please ask your question again, and then we'll stop at that stage.
Hello. Hopefully I don't get cut off again. Can you hear me? Yeah.
Yeah, I can hear you.
Okay. Just a quick question about you, because you compared like two different ways of doping. You did like the gating and also the basically the chemical doping. And your main aim was to basically eliminate the electric field and the confinement, basically, and to identify how that affects play a role. But in terms of like the sodium, where you dope for 1.0 and 0.3, is that the same amount of electrons for chromium? Is that comparable to the gate doping? Like, so you said like for the gate doping, you had 25%, and then for chemical doping, I'm not too sure like how. Much that changed. Yeah.
Okay, so the quick answer is, so first of all, I probably should mention that how we measure this 0.3 or 1.0, that is simply just measure the weight of the crake. And the assumption of the weight of this particular element, sodium, then we can just work out how much percentage of doping compared to this, for example, the amount of the number of the chromium. And we are working on this this carrier doping regime by the transport experiment. Again, it's slightly difficult to make a contact by not breaking the vacuum, but my postdoc and student is working hard. They are working hard to do that. But just simple, weight calculation, we can tell that this is 0.3 and 1.0, and on the assumption that each, sodium produces 1 electron per atom, it's actually 30% of the doping. But again, this is on a very dangerous assumption. So we hope that we can clarify by just doing the transport measurement. So that's what I can tell at this stage.
Okay, excellent. And if you have still time, let me do one last question from Aga. Aga Shahi, can you please ask your question, and then we'll definitely finish then after that. Can you mute yourself? Yeah, go ahead, Aga.
Hello?
Yeah.
My question is, how can you explain double exchange and metallic collector for 100%?
Great. So it's always a great question, and I don't have any clear answer to this. Indeed, maybe just look at this one. So these are contradictory pictures. So by looking at transport, we can clearly say that there's a metallic behavior, which means that you can, electron is continuously, moving with maintaining the momentum, for example. And then, so that in that regime, probably double exchange isn't a right picture. It's already probably itinerant. I'm not sure itinerant is also the right picture, or this like a Pauli paramagnetism is the right picture to explain this, to drive the ferromagnetism. But then what we can tell you that between these two extreme cases, there must be the case where, there are chromium 2+ state, chromium 3+ state, and then this carrier is not fully delocalized, therefore kind of hopping between these two different sites. And at this regime, I'm certain that this double exchange picture should be appropriate to use it. So it's a bit of a boundary that I wouldn't say that everything can be explained by double exchange interaction, but this is something we can induce as a mechanism that can promote further increase of the exchange coupling between the two chromium ions.
Okay, thank you.
Thank you. Well, with this, I think we've reached the end. I'm going to stop the streaming now in here.